What is the origin of the surrounding infinity that we call the universe? Were there periods in its time evolution or places in its immensity where the basic components are not the nuclei composed by nucleons, but their most ultimate constituents, quarks and gluons? Following the cosmological scenario based upon a primordial explosion, matter composed by quarks and gluons is supposed to be the characteristic for the composition of the universe in its very first moments, somewhere to the order of 1/1,000,000th of a second after Big Bang. With the advent of accelerators and large-scale experimental devices, through nucleon-nucleon, nucleon-nucleus, and nucleus-nucleus collisions, finite pieces of nuclear matter at different temperatures and densities can now be produced inside the laboratory. The high complexity and cost of the accelerators, experimental devices, and computing infrastructures specific to this field of research significantly enhanced scientific collaborations all over the world. The Large Hadron Collider is a proton and ion accelerator built near Geneva, Switzerland, between 50 and 175 meters underground. The Large Hadron Collider resides in a circular tunnel roughly 27 kilometers in circumference and runs along the border between Switzerland and France. The final energy, which will be reached at LHC, will be of 7 trillion electron volts for proton beam and 2.76 trillion electron volts for lead nucleus beam. ALICE is the only experiment dedicated to nucleus-nucleus collisions. Although large scientific centers are created around large-scale experimental facilities, the construction and operation of such facilities is largely based on the contributions of participating national laboratories from various countries, where much of the complex detection and identification devices, associated electronics, software packages, and theoretical models are designed, developed, and constructed. Thus, the small centers remain a permanent resource for young, talented specialists and leaders in the field. Let's see how this strategy is followed in the Hadron Physics Department of the National Institute for Physics and Nuclear Engineering. Our team came together during the design and construction of a device for reactions analysis based on complex and unsurpassed line acquisition, otherwise known as Dracula. We embarked on relativistic heavy ion topics, being one of the groups involved in FOPI experiments since the inception of its design phase. In 1999, we became an official member of the ALICE collaboration. ALICE stands for a Large Ion Collider Experiment and is optimized for the study of the collisions of heavy nuclei with an aim to identify the properties of matter that existed within a few microseconds after Big Bang. Based on the contributions of our group to the R&D activities, we received the challenging task of building the ALICE TRD subdetector, together with Gesellschaft für Sphärionenforschung in Darmstadt, Joint Institute for Nuclear Research, Dubna Institute for Kernphysik of Frankfurt University, and Physics Institute of Heidelberg University. 24% of the ALICE TRD chambers were built in Hadron Physics Department. For Romania, this is the most important contribution to come out of a large international collaboration ever. The final preamplifier shaper chip is designed in the 0.35 microns technology, has a number of 16 channels per chip, and its real size is 2 by 3 mm square. Being aware of the computing needs to simulate, calibrate, and analyze the experimental information delivered by such a complex experimental device, our group initiated grid activities in early 2000. By November 2002, based on the computing cluster of the Center of Excellence, NIHAM, the first international grid application in Romania within ALICE Grid came to fruition. Presently, the NIHAM grid site, with more than 2,000 cores and 1.8 petabyte storage capacity, is one of the most efficient ALICE Grid sites, delivering more than 40 mega-hours of computing units over the last 9 years, which represents 5% of ALICE collaboration. Our group is involved in the analysis of PT spectra of charged particles and charged hadrons as a function of charged particle multiplicity and event shape, aiming to identify the production of deconfined matter and collective type phenomena in P+P collisions at LHC energies. We proved for the first time that the tiny object produced in violent P+P collisions, with energy density never before produced in a laboratory, is expanding at a rather similar rate to the universe. Another goal of heavy ion collision experiments at relativistic beam energies is to identify signatures of the partonic phase at large density of nuclei as it is supposed to exist in the cores of neutron stars. The CBM experiment at FAIR will be confronted with a selection of rare probes in high multiplicity environments at collision rates of up to 10 to the 7th events per second. Therefore, a new generation of detectors is required. We embarked on R&D activities for developing high granularity, high counting rate resistive plate counters required for time of flight measurements in CBM experiment. A few RPC prototypes were designed, constructed, and tested. The results showed very good performance in terms of time resolution, granularity, and efficiency in high counting rate environment. For TRD subdetector of the CBM experiment, foreseen to perform charge particle tracking and electron identification, we developed a few TRD architectures. The radioactive source and in-beam tests showed their performance in terms of electron-pion discrimination and two-dimensional position resolution for counting rates similar for CBM experiments. Based on such experimental information introduced in Monte Carlo simulations, a realistic estimate on pion misidentification as a function of number of layers of such TRDs can be obtained. In the same time, it was mandatory to develop the required associated front-end electronics. A new generation of front-end electronics for these detectors based on ASIC was designed in our department, produced at AMS Austria, and successfully tested by members of HPD on the above-mentioned detectors with radioactive sources, mixed beam of electrons and pions at PS and CERN, and reaction products at GSI Darmstadt. How were nuclei built up from their basic constituents? Nucleons? A process that also takes place today in supernova explosions and is another challenging question to be answered. The microscopic many-body models using effective nucleon-nucleon interactions from modern charge-dependent forces are essential for a realistic description of exotic phenomena, highly required by astrophysics scenarios. Hadron Physics Department as a small group focused on potential transfer of some results obtained in our research activities related to basic research towards applied and technological transfer areas. At present, it is focused on multipurpose thin layer deposition technology. For interval working group meetings, seminars, lectures, invited seminars, and video conferences mandatory in our days for an efficient work within large-scale international collaborations in which we are involved, Hadron Physics Department has meeting rooms for each floor and a multipurpose conference room of 160 seats, all equipped with an integrated and highly versatile video conferencing audio-video system. Summer student programs, student visits, diplomas, master and PhD thesis students are organized and coordinated in our department. Most of the mechanical components of the detector prototypes associated with front-end electronics, in-house or in-beam test arrangements are produced in the HPD mechanical workshop. This film is dedicated to the anniversaries which are celebrated this year. For example, the 65th anniversary of the Institute for Atomic Physics, a precursor of the present Institute for Physics and Nuclear Engineering. The 60th anniversary of the Center of European Research Nuclear, CERN. 15th anniversary of our membership in ALICE at CERN. The 10th anniversary of our membership in CBM at FAIR. And our 10th anniversary since the inauguration of the detector lab of our department.